Hi everyone, my name is Sahil Khose, and today we have Rakshit with us, who will be presenting his paper, which was accepted at NeurIPS 2022 this week actually. And the title of the paper is "Pruning Has a Disparate Impact on Model Accuracy." A little intro about Rakshit is he's a master student in privacy engineering at Carnegie Mellon University. His research interests have been in the field of privacy preserving machine learning, trustworthy ML, fairness, interpretability, and causality. This is also his second time on our channel after the sixth presentation of three of his papers in differential privacy. That was in July last year. So it's been more than a year now. And the links for all his socials and the previous video will be down in the description. So you can take it from there.
Um, Thank you, Sahil, for the kind words and the introduction. Um, so hi everyone. I'll be talking about pruning has a disparate impact on model accuracy. And this paper was in collaboration with Kwong, who is a PhD student at Syracuse under Ferdinando Fioretto or Nando. And and we also have another professor as a collaborator who works on distributed systems and machine learning within systems architectures as well. And this paper talks about pruning. So for people who might not have any introduction on what pruning is, I came across this really nice blog that explains what pruning is. So here, um, imagine you have a fully connected network and you have connections from all the way from the input to the output, and each neuron affects each other neuron in the next layer. And that you have this fully connected network, we want to find out how can you extract a subnetwork that also has a comparable performance to the original network that you have. So the idea is to compress the network, and if you do compress the model, you save on storage costs, and you also save on computational resources, and you also make them easily deployable for real world scenarios. So most of these models that you see on devices, on your edge devices, such as mobile phones or maybe even IoT devices and embedded systems, they usually use compressed models in such a setting. And so pruning, exactly what it means is that you really want to find out what kind of connections that you have um, between the input and the output layers. In order to find these um, really good connections, you really want to prune out the not so important connections. You really want to skip or remove them just by making their weights as zero, or maybe just removing the weights entirely. So you can do this in two ways. So unstructured pruning and structured pruning. So unstructured pruning is where you have the entire model that is ready for you, and you take the model itself and then you sort out the weights of the entire model. And once you do uh, sort out the weights, you specify this pruning parameter. So let's say you want 50% of the weights to be pruned. That means that you want your entire model to remove like the lowest 50% of your weights. So after sorting it, you remove the lowest 50% of the connections, and then what you have left is the important 50%, the other 50% which is left, and that in itself becomes your compressed model as such. And that's what unstructured pruning stands for. And structured pruning is layer wise. So you can also specify your pruning parameter to be 50% within a particular layer itself. So let's say here, if it's 50%, you have 6 neurons, right, in the input layer. So this means that only 3 of them are activated, while the other yeah or while the other three, if there were 6 neurons, then the other three wouldn't have been activated. But yeah, here you can see, I think it's like, yeah, I don't know what what pruning parameter they put here, but this is essentially the idea of unstructured and structured pruning. So structured is layer wise and unstructured is over the entire model itself. And in pruning, what you do is that you basically remove the weight connections, and you do that by setting them to zero. And if you do set them to zero, you basically are compressing the network. Yeah.
Yeah, quick questions on the pruning part.
Sure.
So in the unstructured part, we make the assumption that the lower activations for the weights are
Mhm.
like unimportant for us, right?
Um, for the unstructured part,
Yeah. Because we sort it and then we just drop the low activations.
yep, right, yep, yeah.
Right.
So what we do is we sort them out, and whatever's the lowest X percentage of the weights and the
Hmm.
activation is just removed. Yeah.
Yeah. And for structural pruning, it would be something. So we are dropping nodes there, like we do in dropout, but we are dropping them permanently.
Yeah, so here also you're kind of dropping out the all the connections with respect to that particular node. Yeah,
Okay.
so yeah, that's what layer-wise pruning means. Yep,
Okay. So in dropout, the entire node will be removed, but here percentage of the connections are removed.
right. Yeah,
Right. Makes sense. All right.
exactly. Yeah, and yeah, now that I've given you a sense of what pruning is, so we try to tackle the idea of fairness, the unfairness in pruning, and we observed that as you um, just one second. Yeah, here, yeah, as you increase your pruning parameters, uh, you also observe unfairness. So what happens is that your majority class is, I mean, your model is like more representative of your majority class than the minority class. So out here, if you see the diagram, here we have no pruning at all, and you see that the accuracy for others is like nearly 20%. But then as you increase the pruning rate, the pruning parameter, when you go to 90%, you see that others literally has zero accuracy. It just goes down from 20% to zero accuracy. And here, if you look at the white race, yeah, for no pruning, it's like 80%. And then here it increases to like 85%. So what happens is that your majority, um, so what happens is that it's called a Matthew effect. So your rich get richer and poor get poorer. And this kind of effect has been observed in practice in other papers as well, such as differential privacy has a disparate impact on model accuracy. And that's where we got our name of the paper. Yep. And yeah, um, yes. Before before I move on, yeah. So I also want to say that we wanted to observe this difference, and this was our motivation. And we also wanted to analyze why this disparity actually occurs in practice. And we came up with like a theory saying that um, this um, this disparity usually occurs because of the disparity between gradient norms and also the disparity between Hessian norms. And for those who don't know what Hessian norms mean, they are basically double derivatives. Yeah, double derivatives of the gradient itself. So yeah, if the gradient is like single derivative, Hessian is like double derivatives. Yeah, so we use the Hessian matrices, and we also calculate the out here in our paper we looked at uh, the eigenvalues of the Hessian matrices, but um, yeah, but I think there is still some scope in looking into like the trace of the Hessian matrices, and also like other properties of Hessian matrices or gradient norms itself, that could shed light on how unfairness could possibly be exacerbated. Yeah. um, yeah, apart from that, these findings are obviously significant because pruning is right now deployed everywhere in like prune models are deployed in edge devices for either security cameras and also like autonomous devices for applications such as facial recognition. And yeah, so fairness in these settings are like essential. And if fairness is not tackled, then it might have profound effects on our society and economy as well. So yeah, and here we have the related work section where we talked about like where fairness and network pruning have been studied before, but then most of them have been talked in empirical nature. So a lot of them just shows experiments such as this, showing that okay, this happens in practice, but then none of them investigate like why this exactly happens. And here we came up with some theory to show that this happens because of the disparity between gradient norms and Hessian norms. Yeah, and when we come to the problem setting, um, what we want to obviously minimize for the is this function. So basically, you just want to learn some kind of a predictor, and this predictor tries to optimize for this function. And this function is a very basic loss function that we usually have in machine learning. And out here, what we want to look at is the fairness definition that we proposed. So here, the fairness definition that we proposed is based on excessive loss. So excessive loss is the difference between the original and the pruned risk functions. So you can imagine, like, if you take the loss of the original model for some particular group versus the loss of the um, pruned model for that particular group, and that gives you the excessive loss of that particular group. And with respect to that, we also came up with a fairness violation. So the a fairness violation is like an extension of the excessive loss metric that we came up with. So you can think of this as um, the maximum. Um, so the fairness violation of a data set would be the maximum difference between the excessive loss between two different groups within that particular data set. So you could take like so if you look at this data set, if I take the white race and the others race, um, yeah, and others, um, so this would give me the max difference, right? Because here you have like 85% and here you have like 0.85 and here you have like 0. So in essence, this should in essence give you like the biggest difference between um yeah between RA and R of A dash. Yeah.
Uh, yeah,
That-
just to clarify, the fairness would be, so excessive loss would be the change in loss from
yep.
your original model to the pruned model.
Yep.
So that is one delta. And in this case, as you said, before pruning it was 80%, and after pruning it was 85%. So that would be negative 5%,
Mhm. Yeah.
right?
So we take the mod of it. Yeah.
Yeah. And then you're comparing, so R of A of, so R of white would be minus 5%. And because it's actually increased when you expect it to, no, it would increase in the case of majority groups and it would decrease in the case of minority groups, right? Because of the
Right.
Matthew principle.
Right. Yeah.
And for the our our others would be from, it went from 18% to almost 0%. So that would be positive 18%.
Right. Yeah.
So that delta would be, so your fairness violation would be negative 5, negative 18, that's just 23%.
Exactly. Yeah, that will
Right.
give you the max thing. So out here, if you look at 23 might be the max thing because if you look at the other the change in other graphs, it's not too
Mm.
much. But I think if you look at the black race, I think that also has like a very good change from point. This actually drops down from 0.75 to I
Yeah.
think point 0.2 or something like that. So that in itself, like R of A for that group would be, I think like zero point 0.6 or zero point
Mm.
0.7, which is like greater than what you had for others. Yeah,
Yeah.
like in the previous case. Yeah. So you calculate this for like each and every group, and then yeah, and then you categorize that delta as the maximum difference that you get for the excessive loss functions.
So what would both of them symbolize, the excessive loss and the fairness violation?
So the excessive loss just tells you like how much you're deviating from the original model. So you're trying to say that uh, how much excess, like as the name suggests, you're trying to say that what is the change in loss or the some kind of a change in accuracy uh,
Mm.
that the group in itself is experiencing with respect to the original model and the pruned model as such. Yeah, and how much does that change either exacerbate or does it alleviate and or so on. Yeah, and here with this delta you're trying to say that you're trying to find which groups result in the most difference as such.
Okay.
So yeah, using these two groups A and A dash, you can say that what is the maximum fairness violation that I could get with this particular data set containing these
Right.
samples. Yeah.
Right.
Yeah.
So ideally, what this maximum would be that R of A has to be the largest increase in a group, and then R of A dash has to be the largest decrease in the group, and that's what the matching principle is taking place in.
Right. Yeah. This is what the fairness violation comes in. Yeah,
Got
that's how your fairness is getting violated. But then in essence, we want to mitigate this. Yeah. And we want our fairness violation to be zero, as you can see here. So your pure fairness you can only achieve when it's zero. That is, no matter what kind of group you take, you shouldn't be able to like get any excessive loss as such. Like you shouldn't be getting any delta as such. And a fair pruning method, like it tries to minimize this kind of an objective. Yeah, and this is why we came up with yeah, certain theory saying that why R of A is actually greater than zero. um so R of A here is the loss function, right, the excessive loss. And we also wanted to see like why R of A is sometimes greater than R of A dash for some particular groups, or the other, or vice versa for other groups.
it.
Yeah, right. Yeah, and this was our motivation. And out here we had some theorems um, on why on what R of A is and what does it depend on. And here I think the main takeaway from this is you can see the R of A is kind of proportional to the gradient norms G, and also proportional um, to the eigenvalues of the Hessian matrix. So this is symbolized by lambda of H, and you can yeah, we have a proof for that using Newton-Raphson's method that we learned in like 11th standard, and also um, yeah, also Cauchy-Schwarz inequality. Yeah, yeah, these were some stuff that I had learned in my undergrad, but then this was the first time that I actually saw that uh, being useful, yeah, in practice.
Yeah.
Yep. And then apart from that, we also came up with like some corollaries saying that um yep, here as I said earlier as well, that certain groups might have um um like certain models, like for example, like if you have one particular group, so out here what we are trying to say is that if you fix a particular group, um you might uh you for the original model loss might be like it could be greater in some sense. So let me say that if k dash, so if k hat, or I don't know what to call it, k bar, okay, let's call it k bar. So k bar is lesser than k bar dash. So this means that the former model, it has lesser parameters than k bar dash. So um,
What's K in this?
so k bar and k bar dash are basically like a parameter size of
Okay.
the yeah, you can just think of it as model parameters as such.
Okay.
And yeah, so k bar, if k bar is lesser than k bar dash, this means that k bar is the prune model, while
Mm.
k bar dash is the original model. So the k bar dash would obviously have like a lesser loss with respect to the um
K dash.
K bar, because K bar here is the prune model, and the prune model is supposed to have higher loss and lesser accuracy with respect to the original model. And that's basically what we say out here.
But
And
that is with respect to only the underrepresented groups, right? Because it would be the reverse. So it was the reverse in the white case that we saw earlier in figure one.
right. Yep. This is only for the lesser known groups as such, like the minority groups. But I think uh, this also might be satisfied by the majority groups as well.
Yeah.
So this is because we are talking about loss. So loss could change, not drastically, but it could change like in a minute fashion, and um, yeah, that could still represent the disparity out here. Yep.
Right, right. I think our comparison earlier was also inaccurate. I just see that its accuracy and all of these metrics were in loss. You were just
Yeah.
correlating loss and accuracy as the same thing.
Right. Yeah. I guess I shouldn't have done that. But then here we usually talk about loss as well.
Yeah.
I mean, we only talk about loss
Yeah.
as a metric, but in the graphs that we show, we also show, instead of showing
Accurate.
loss, we show accuracy. Yeah.
Great.
People like seeing accuracy graphs. Yeah.
Yeah, but the on like theoretically, like just for conceptualization, that was correct. But
Right.
the
Yep.
like the use case of the formula was different.
Yep.
It is not on accuracy; it's on the loss.
It's from the loss. Yep. Exactly. Um, yeah. And continuing to the next section. So in the next section we talk about um here. So this proposition is the one that I wanted to talk about, saying that if you have one group in your data set uh, having more samples than another group, DB, so you can say that the gradient norm for the minority group is sorry, the gradient norm for the majority group is like lesser than or equal to the gradient norm of the minority group. So we also had a plot showing this. So if you have the group size, so you can see the group size in maroon, and as it decreases, your gradient norms actually increase. So yeah,
So this could be the gradient norm during the pruning process.
during the pruning process. Yep.
Right.
Actually, here we don't even talk about pruning. It doesn't need to be pruning as such. Like we are just talking about the model out here. So, like the original model without any pruning.
So
So,
gradient norm, how will it be calculated?
so the gradient norm is calculated by using the loss. I think. So I think autograd. I think there's a function in Torch called autograd, and that
Mhm.
in using it, you can just calculate the gradient very easily by just calling torch.grad. Yeah. Uh,
Yeah, I just meant like we train the entire model, and this is the gradient at the end of the pre-trained model, the trained model.
yep. Yep. That's pretty much it. Yeah.
Okay, so even after it's been fully trained on the entire non-pruned network, the gradients for larger group sizes is smaller than gradients for smaller group
Right. Yep. Yeah.
sizes. Right.
This is without any pruning as well. So um, here we just want to see like why disparity in groups gradients actually causes unfairness. So yeah, you can see that it just depends on your group size, and also like yeah, that in effect that affects your gradient norms as such.
Right.
And
So
yeah,
will
we
the intuition be that the model has already it's only optimizing on the loss? So the more represented groups are already very quickly learned by the model because that's what fetching the most accuracy.
Mhm.
Hence, it
Right.
does not want to change those weights, but when it comes to the smaller groups, it wants to change those weights because to get higher accuracy.
Exactly. Yep. I mean, you put it in really good words. I would say that I would add to that saying that your minority groups are like very sensitive also. So this actually this actually makes them um, change very frequently, like in the sense that uh, since you've already learned a lot about your majority class because you have too many samples on it, so if because you have like very less samples of the minority class, it's very sensitive to like uh, change as such as well. Yeah, I think I think there are like a lot of future directions that we could explore on like not only fairness but also looking at like robustness within like minority classes and majority classes as well. But yeah, you really bring up a good point. Mhm.
Awesome.
Yeah, yeah. Apart from that, yeah, we have another figure on accuracy and gradient norms and group Hessians. I really like the group Hessians graph. It looks like Burj Khalifa. Yeah. Yeah.
So what do these diagrams represent?
Oh, these diagrams represent like for different pruning rates, what exactly is the accuracy and what exactly is the gradient norms. And as you can see that your gradient norms are like they kind of increase with respect to the group size. So I mean they decrease with respect to the group size, and if you have like a lesser group size, you would have a higher gradient norm, which is kind of observed for all the pruning rates as well. And for Hessian norms, you kind of see this graph where um yeah, I'll talk about Hessian norms in some time. Yeah,
Uh,
there's another graph that I
can
really
we
want.
just go back to the figure? I think what are no figure for itself.
Oh, okay, figure four, okay.
Yeah. So there are some peaks for in the B section. There are some peaks for higher pruning in Black,
Right.
Asian, and Indian. So what is this anomaly here?
Yeah, this is kind of weird that we observed this. So we actually ran our experiment for, uh, I think, 3 times, and we still observed that like Black Asians and Indians were still getting like higher gradient norms. Yeah, but this is still remains unexplored. Like we still don't know why this is happening. Maybe it might have been like, um, I don't know. It could have been like other external factors as well. Maybe like um I don't know, maybe too much noise or something, or maybe like too much, um, or maybe the implementation as such maybe was like, um, yeah, the implementation of calculating gradient norm was like not very optimized, because calculating gradient norms and Hessian norms is like it takes up a lot of time and a lot of compute. So you actually have to like approximate your Hessian norms in order to like actually calculate it. So that was something that was really hard for me, because in order to like run our experiments, we to calculate the Hessian norm, since it's a double derivative, I need to first calculate like the gradient norm, and then on top of that I need to calculate another derivative. So it takes up like an order of magnitude when it
Mm.
comes to like computational time. But yeah, with respect to these differences, yeah, this still remains to be unexplored. Yeah.
But there is no, like, it does not reflect. So I think only 70% and 70, 80, and 90% pruned models are showing that in the gradient
Right.
term, but that doesn't reflect in the group Hessian. They look, they don't
Right.
look same.
Yep. It's only for the gradient norms, which is
Mm.
kind of weird. Yeah.
Correct.
Yeah. Mhm. Yeah, I think that needs to be explored as well. Like, because um, if you see like the white and others as well, you can see it decreasing, but it's only
Mm.
for the Black, Asian, and Indian, which is like kind of increasing. Yeah. But yeah, that's a good catch. Um, yeah. So moving forth, um, yeah, here we looked at like gradient norms, and here we also try to say that you can upper bound your gradient norm to a particular accuracy. I mean, using the big O notation, you can say that, yeah, um, you can kind of upper bound it to that particular accuracy, like f theta star of x minus y. And yep, there's another graph on accuracy versus gradient norms. So as you can see, like as your accuracy decreases, um, your your gradient norms increase. So you can think about it in terms of figure 2, where if your group size is like lower, so your accuracy is also lower, and this also results in like um, higher gradient norms. Yeah. Yeah. Apart from that, um, yeah, in another section we talked about the Hessian norms. So out here we came up with one theorem which says that your Hessian norms is like related to the distance to decision boundary, and also proportional to the accuracy as well. So if we look at this graph, so here we looked at the lambda of the Hessian matrix, which is the maximum eigenvalue for that particular Hessian matrix that we calculate over that particular group A. Okay. And in this figure, we looked at the group Hessians, and we also looked at the distance to decision boundary, and also like the accuracy. So if you do look at the distance to decision boundary for i- like the minority classes, it's what happens is that you quickly reach the decision boundary, but for the majority classes, it still takes time for it to reach the decision boundary as such, um, which is like kind of intuitive, but yeah, we observed this in practice, and also finally showed
How do you
that.
calculate the distance between the distance boundary? What does it represent? I was
Yeah,
wondering.
that's a good question. So out here, what we used was the if you take the softmax outputs, you basically take um, the maximum softmax output minus the uh, minus the second maximum softmax output. Does that make sense?
Yeah,
Um,
that like when we calculate top two, so like the highest activation for that particular class and the second.
Right, highest minus the second highest,
Mm.
basically. Yeah, the norm of that. Yeah.
Okay. So what does this represent? Like higher represented groups
Yeah,
have that
this means that higher represented groups are like um, it gets much more easier to like quantify it um, to be that particular group. So it's very easy for it to say that say
higher confidence basically.
the higher
Not
confidence.
necessarily, but the softmax is in such a way that it model thinks it's of a higher confidence.
Mhm. Right, right. So what I'm trying to say is that if imagine you have this network and imagine you give this give the network a white image like a person from a white race, and it's easier for it to calculate, um, easier in the sense that it's uh, yeah, it has higher confidence for it to like classify it as a high like as a white race rather than when you take an Indian like a person who's an Indian and use that image for testing. So basically if you have like an image of a person with a white race, it's the its confidence is like much greater than when you take from an image of a person who's an Indian race and feed it to the same model. Yeah. Does that make sense?
Yeah, yeah, that's pretty intuitive because of the
Yeah.
Hessian as well. Because you'll have less Hessian for higher represented group or higher accuracy groups, and hence it'll be more confident about that particular prediction.
Mm-hmm. Right, right. Yeah. Yeah. And this is also like proportional to accuracy. So you can see that the accuracy is all that also like kind of decreasing. Yeah. And yeah, here you can see a graph for Hessian norms and also like the gradient norms. And we observe that both of them kind of increase as you like increase your yeah, as you like decrease your population size for that particular group. So if you see the others groups actually has like higher gradient norms and higher Hessian norms as we highlighted before as well. And yep. And apart from that, because we saw this disparity between Hessian and gradient norms, so we came up with a very simple mitigation solution. So what you would do is that once you have a prune model, you would want to optimize for this objective where you try to minimize the loss such that your gradient norms are equalized and your Hessian norms are equalized to that particular group. So for example, if I take like the if I take the others race, like if I take others because I know that um, the gradient norms here are like a lot more or a lot more, right? And if I equate that to be equal to the gradient norms of the entire model itself, and if I try to minimize for the loss by fine tuning it again, fine tuning the pre-trained model, I could I could basically preserve on yeah, I could basically not exacerbate the unfairness. I would get a much more fair method because I'm kind of learning equally. Yeah, I
Mhm.
know this is a really bad term, like a really bad way to put it, but then um, in order for you to visualize, I think this diagram might help you. So out here, what we do is that this is what you have with so the top row is with the original model, and here you can see that you have the gradient norms which are like increasing across the different groups while the decision boundary is like decreasing. But for the bottom row, what we do is we implement the fair method that we suggested before, where you like equalize the gradient norms and also the Hessian norms. So you observe that the decision boundary is kind of equal for all the groups, and the gradient norms as well as is like equal to for all the groups. And here you can see the accuracy also doesn't deviate as much, and you also see that your standard deviation between like two different groups like the maximum and the minimum is like much lesser than what you had earlier. Here you had like zero point 0.8 and point I don't know 0.15. So this difference is obviously higher than zero point 0.6 and like
Yeah.
0.3. Yeah. And this is like one mitigation solution that we came up with.
But was the overall accuracy same or less when you use this technique?
Yeah, that's a good question. So the overall accuracy is like obviously lesser, but then you preserve on fairness. Yeah. So we looked at fairness as a constraint and then optimize for that objective. Yeah. Yeah. This obviously has lesser accuracy, but yeah, it doesn't take too much of a hit. Yeah.
Mm.
And yeah, so what we observed in practice was that so calculating Hessian norms and gradient norms is not feasible, obviously. Yeah, and yeah, so the shortcoming of our approach is that uh, so you actually have to like do it by an order magnitude for all these deep and over parameterized networks. So we came up with another simple solution, which is like adopted in many domain generalization papers and also in like other fairness papers. So what you do is that you try to just minimize for this objective. Um, so what you do is you just assign the loss of the yeah of a particular group to be equal uh, to the entire m- for the loss of the entire model. So you try to minimize for the loss such that the loss for that particular group is like equal to the loss of that particular model as such. So you fine tune your prune model by satisfying this kind of constraint. And this is much easier to solve because calculation of losses is like much easier when you compare it to the group Hessians or the group gradients.
Yeah.
Yeah.
One question I have in equation 7 is why did you try to equate both the gradient norms and the Hessian norms? Couldn't you just do it with gradient norms?
That's
Because it's
that's a good question. So some of our reviewers also asked the same question, saying that why don't you relax like one of the constraints? And we actually tried that out, and yeah, that is possible, and that actually gives you uh, fair results as well. And yeah, we have the relaxed approach as well. We have some results in a table that we put up on open review. So once it's out, I think uh, yeah, I think you can see it. But yeah, that is entirely possible. And I think that might be a better approach out here. But yeah, again, calculating gradient norms is still
it's
uh,
still expensive.
yeah, it takes more time than calculating the loss. Loss is much easier. Yeah.
Yeah. Another question about the equation 8. How would you like in implementation? How would you equate this loss for the entire model loss?
Good question. So in implementation, what we do is we calculate the fairness violation. So using fairness violation, we actually categorize the fairness violation of each of these groups, and whichever has like the highest fairness violation, we try to like assign the loss to be like that particular yeah, to be like that particular loss as such for that particular iteration. Yeah, it's a little confusing, like the implementation. It took me like some time to understand it. Yeah. And there was like one more parameter called fairness violation, which we actually discussed earlier.
Hmm.
But yeah, this it's not discussed out here because this actually comes from Nando's earlier papers
Hmm.
where they explore like Lagrangian duality and so on and so forth. So they have this regularization term, and this regularization term actually comes from it's kind of synonymous to what we have for the fairness violation constraint here. Yeah.
Understood.
Mhm. Yeah, apart from that, there are a few results. So what we do is that here there are four settings. So one is where you perform no mitigation at all, and one is where you have like fair before pruning. So what you do is that you would make your model, you would just fine tune your model without before like even pruning as well. And after fine tuning your model with respect to that constraint that we observed, uh, equation 8, then you would prune your model. So that's called fairness before pruning. And fairness after pruning is basically when we apply the mitigation solution, like after pruning your model. And fairness both refers to when you actually perform the pruning and fine tuning. Um, yeah, like fairness, like you would fine tune it fairly, and then you would also like prune and fine tune it fairly. Yeah. So there were like 4 different experiments that we had to run, and here are the results. And as you can see, I think it's very intuitive that the fairness both and fairness after pruning result in lesser fairness violations, and yeah, lesser fairness violations for higher pruning rates. And this is what we wanted. Yeah. And this is kind of intuitive because fairness both incorporates both training like fairly and also like pruning and fine tuning fairly, while fairness after pruning is like after you prune the model, you since you have the pruning constraint already set up, you basically would want to fine tune over that uh, new set of pruned uh, the new pruned set of model that you get, the new pruned model that you get. And yeah, but after fine tuning fairly over the pruned model, yeah, this is kind of the result that you get. So uh, so our results show that the pruned after fine tuning and pruned and fairness in both, sorry, fair after pruning and then fair both give like really good results. Yeah. That's pretty much it, I guess. And then apart from that, um yeah. um
So what we observe is fair before pruning does not necessarily give the same output because the mitigation is before the pruning step. So the pruning does not take care of the mitigation part. That's why.
right, yeah. Yeah, we also discussed this, like why this happens. So we say that like fairness after pruning is like it achieves like better fairness violations as such, like after you like prune it, and especially at higher pruning regimes, as you saw. So this is because like the resulting model has like lower differences in like gradient norms and group Hessians. Yeah, so that's why you have like um yeah, because the fair training that's observed. So what you're doing in fair before pruning is that you're training fairly and then just pruning it, rather than but in fair after pruning, what you're doing is that you're pruning and then you're gonna train it fairly, right? So
Exactly.
uh, because in fair after pruning you would have like like low differences in gradient norms and Hessian norms. This actually results in like less disparity as such as, so it's better. Yeah.
I agree.
Yeah. And yeah, yeah, there are some limitations as well. um yeah, as I said earlier, it's really hard to calculate your gradient norms and Hessian norms. So also like for if you have large models, yeah, this is like very it's computationally infeasible. And apart from that, there were some um there were some other aspects that we thought about. Yeah, such as like pruning might have like a negative impact on like adversarial robustness, like there was papers about it. And yeah, so there's a lot to be done within the compression model space, because people are now starting to think about robustness, fairness, interpretability, um, yeah, and so on and so forth, within the compressed ML space. Yeah. And yeah, finding the hyperparameters were also like really hard because you had a lot of experiments to run, and running these experiments took a lot of time. And yeah,
What
finally,
was the model size that you were using in this paper?
oh, here we were using ResNet 18, ResNet 18 or ResNet 50. Yeah, yeah. But then there were also some results on VGG 19, I think, that we displayed in the appendix. Yeah. But yeah, apart from that, the main takeaway from this paper is just the pruning. We just showed theoretically like um, why pruning causes unfairness, and this is due to the disparity in gradient norms and also the disparity between the Hessian norms. And using because of these factors, we just try to show that what could be some possible way to mitigate this, mitigate unfairness in pruning. Yeah.
Yeah.
Um, I think that's pretty much it. Like there are proofs and other experiments like later on. Yeah.
Just one question. How was the difference? I think you might have mentioned it, but it slipped my mind. What was the difference in both the methods, like equation 7 and 8, for mitigating?
Right. Um, so yeah, do you want to like see the results, Sachin?
Yeah, anything works. So like, how was like which one was better? And to optimize, obviously the say equation 8 is easier, but how were the
Right.
results?
Yep. So this was these were the results that we had for full. So full mitigation is the one with both the gradient norms and the Hessian norms, while relaxed is like um yeah, I think relaxed is like you only use the um only one of them, if I'm not wrong. Wait,
Mm.
let me just check this out. Yeah. Um. Yeah. Okay. So relaxed is basically equation 8, and full is equation 7. Yeah. We still need to look at the relaxed version of the full, because in the full we have two constraints, right? So
Yeah.
maybe just dropping one of them is yeah, one of the reviewers suggested that to be included in the full paper later on. Yeah.
So what was the like what were the metrics when doing both of
So out
them?
here we just looked at accuracy, and so you can see that with the full version you get like 0.395, and with the relaxed version is like 0.39.
Mm.
So there's not much difference. Yeah, it's literally like statistically insignificant. Yeah.
Mm.
And yeah, if you look at like the difference is not too much, but then the only difference between both of these methods is that the computational time. So it takes a lot of time to like calculate the Hessian norms and gradient norms in the full version. And we also mentioned that, saying that the running time of the full version is like largely, it's much longer than the relaxed counterpart. And this is due to the calculation of like the gradient norms and the Hessian terms. Yeah.
And how was the excessive loss and all of those metrics for both of these versions?
Um, Yeah, that's a good question. We don't look at like has excessive loss as a metric as such, even though like
Mm.
we proposed it. So we proposed it because of the theory that was involved.
Uh,
But in order to show the experiments, we looked at accuracy because, uh, yeah, because people in literature usually think about accuracy and loss to be like synonymous. But I know they aren't. But yes,
yeah.
yeah.
So coming back to accuracy, was the representation of underrepresented classes similar, or how did it deviate? At least the overall accuracy seems to be equal.
Yeah, the overall accuracy seems to be equal, and even for the underrepresented groups, they weren't that bad as well. So here you can see, I think with UTK gender, I think the female is like the um, underrepresented group. So in the
Relaxed.
so yeah, in the relaxed version you see 0.845, and in the full version you see 0.876. But when you're going to calculate the overall accuracy, in the full version it's like 0.857, and in the relaxed version it's 0.852. So
Mm.
the difference is not too much, to be honest. And so it's so that's why we suggested uh, to use the relaxed version rather than the full version, because of the running time. Yeah.
Yeah, that makes sense.
Yep. um yeah. And any other questions?
No, that's all I think. It was like a very nice presentation, and yeah, the discussion was great. It really helped get like deeper understanding of the paper.
Sure. Uh-huh.
What are like, are you planning on any future works for this, or yeah, what are plans for this paper?
Oh yeah, sure. So there's so this semester at CMU I'm doing an independent study with Professor Zachary Lipton, and yeah, and one of his PhD students called Pratyush Maini. And Pratyush has made really good works at UAI, ICLR, and also NeurIPS this year. And Zach is very well known in the field for interpretability. So we are planning to think of like pruning as a regularization method, and maybe what if we could like use pruning, and then also using pruning to preserve privacy as such. And we're still thinking on some directions related to that. But yeah, that's part of my independent study. So it's part of my course. And yeah, apart from that, there's also the paper that we are looking at, like Sahil and we are looking at like counterfactual tickets. Like what if you have like different subnetworks um, within your original model, and these subnetworks could result in like different your different classifications as such for yeah, for a particular test sample that's tested on these different winning tickets that you get from the lottery ticket hypotheses. Yeah, this is one direction that we are looking at, and there's another direction that we are looking at um, on investigating membership inference attacks in compressed models. Yeah, um, yeah. So I think uh, this field is booming right now. A lot of people are trying to think of compression models and privacy as well. And there was a paper at NeurIPS again this year, called differentially private model compression. Yeah, by Fatima, and yeah, she did that work, I think, when she was in Microsoft Research, and it's a really cool work. And yeah, you should probably check it out. I think the preprint is already out. Yeah.
Yeah. Now a bit unrelated question, like not so technical question. Like, what was it like when you heard the news of your first conference paper acceptance, and that too in like the best conference, AI conference out there?
Um, yeah, I was kind of elated because yeah, the thing is that to be honest, like um I wasn't very sure of even working on this paper. So I started working on this paper, I think, in mid-April. So I so Nando was really kind enough for me to like join in and contribute to the project. And yeah, all the graphs that you see are also like um, yeah, like all the experiments and everything were like run by me within like just 1 month. So yeah, I had to like dive into a new project entirely, and all the theory and everything was set up. It was just running experiments. So I had to like jump in and then contribute as fast as I could, like I right. And that was really hard. And I took up like so much of my time just trying to understand like what needs to be done. And luckily, I had some background in pruning because I had taken this course called ML with large data sets during my first semester at CMU. And yeah, and that in that course, we actually were taught about pruning and lottery ticket hypotheses. And also, yeah, our actually final project was basically like a Kaggle data science competition. And we were supposed, and there was the score that they assigned to. So basically, you would want to get a good accuracy on CIFAR 10, and by also pruning the most amount of weights, right? So they had the score function set up, and whoever got the top three got like +5 grades or something like that, like a bonus +5 or something like that. And I think we came fifth in the entire yeah,
Wow.
yeah, across all the teams. I think there were like 50 plus teams, but coming fifth also, it was like a very good achievement because we tried out like many pruning methods, like random pruning, magnitude based pruning, LTH, like lottery ticket hypothesis, and so on. Yeah, it was a fun experience. Yeah.
Yeah, awesome. Uh, Going like you mentioned, like how you jumped into this project in the last minute and you had to pick everything up. So,
Right.
how is your journey been through research? When did you start, and what's your story?
Um, yeah, so I started out my research back in 2020, like just 2 years. Yeah, I was, yeah, when I got my NeurIPS acceptance, like I was actually like quite excited because I think like I would have never imagined like 2 years ago being in this stage of my life, literally. Yeah, because I think the first time like when I started out on a research project, I think I took like 2 or 3 months, like just working on a very simple idea. But then understanding that simple idea was like it took me so long. And it just clicked to me like one morning saying that, okay, oh, I need to do this. And then after that, yeah, after that it was like it was a piece of cake in that sense because once it does click to you, you know what to do. And yeah, because if you know what to do, then I think you should be successful. Yes. So that was my research journey. So I started off with that project, and then soon I started off with XAI, and then I moved on to privacy, differential privacy, and then federated learning, and also um, yeah, now I'm trying to look at um, fairness and fairness, and also I'm trying to look at causality as well, because I feel causality right now is also a really cool topic, and it's booming as well. I think there were like 60 papers, if I'm not wrong, um, that were accepted at NeurIPS this year on causality.
Oh, that's huge.
Yeah.
And how's your experience been in like as we know, like research, it's a very long process. Even after you get the solution, you not necessarily convey the point across, and it's a journey, a roller coaster of accepts and rejects, all of that. So how was your experience being in that?
Um, yeah, that's a good question. So, for me, like I understand that there might be like certain rejects, and even I've gotten my fair share of rejects, to be honest. But yeah, I think it just matters to persevere and persist through all of them, because sure, it might get rejected at one place, but then uh, it possibly could get accepted at another place. So you always have that option to submit elsewhere, like revise based on the comments that you received, and submit elsewhere as well. Yeah.
Yeah, awesome. And do you have any tips for like an upcoming researchers, or what would you do differently if you were starting all over again like 2 years back?
Oh,
And additionally, just last addition, what are the key things that are vital for a good researcher?
yeah, that's a really good question. So I really think that making connections, like networking, is like a very underrated skill in research. So I think that if you have the opportunity to like attend any conference or like network with like other researchers, or even like just talk to them, because I think you'd bounce off a lot of ideas, and also engage in like many meaningful conversations with them, and also like that could help you mature in some sense, mature uh, in terms of like research thinking, and also yeah, and also you could possibly get some kind of a referral or something like that from the opportunity, or some other opportunities that you get through that interactions with other people. So I think networking is a very underrated skill in research, and I think it should be yeah, I think if collaborations do need to go well, you need to like network a lot. Yeah. And yeah, I guess that would have been something that I would do differently if I was, yeah, 2 years back. But yeah.
Awesome. And what exactly, like, what are the steps that we take into this direction? Like, how do you network well? How is it for you?
But so you can actually attend conferences if you don't want to. If it's like impossible for you to attend conferences, you could like shoot up emails to like PhD students, and students or master students. They usually like people like reaching out to you and engaging. Like if they find people engaging with your work, you feel like you've done your part to the society. So that's why people uh like so that's why PhD students and master students, they like engaging with like people who are like junior to them, and try to mentor them and try to uplift them as well. And yeah, I think just gaining the access to like um a portal, in some sense you can think of it like a portal for you to talk to some PhD student that is on the other side of the tunnel or something like that. And once you do establish that connection, I think I think that says a lot. Yeah.
Yeah, awesome. I think that was this became very quick and smooth for us, especially because of COVID, because all the conferences were online.
Right. Yep.
And that became a thing that we could, even sitting in India, we could attend these conferences virtually, and a lot of them also provided waivers for finances.
Right. Yep. Uh-huh.
Yeah, awesome. Apart from that, so you mentioned that condition did play a huge role in your part as a researcher as well. So, want to give any shout outs for someone who's played a major role? till
Oh yeah, sure. I want to give a shout out to Hao Fan Wang, especially because I that was like the first project that I worked with, and it took me like 3 months, I think, just to like get a good intuition on what exactly the idea was, uh, what exactly the idea was on, and what exactly I was working on. And once it did click to me, I was like able to make quick progress. And apart from that, I also want to thank Fatima Sadat Merishkala, because yeah, she helped me a lot, especially with her collaborative efforts. And I reached out to her with respect to a doubt, and then we kept our conversations going, and we still collaborate a lot on um, yeah, on a lot of things. And I have most of my papers with her as well, and she's a PhD student at UCSD right now. And apart from that, there are other people, um, such as Nando as well. Nando has been like really helpful, and yeah, he gave me a pathway to like for uh, for me to get my first conference acceptance at NeurIPS tattoo, and which is amazingly crazy. Yeah, yeah.
yeah, that's awesome. And just one last question before we wrap this up. What plans do you have going forward from this paper acceptance and just in career? What do you want to
In terms of career, or in terms of like
do?
um
Like short term as well and long term as well. What plans do you
Oh, in terms of this paper, I said that we were discussing some other directions with
have?
respect to pruning. So yeah, that is something that we want to do in the short term. But yeah, long.
I actually meant in a personal scale, not related to the
Oh,
paper.
okay. Oh, okay, sure. Yeah. So I actually want to like apply to PhD positions. Uh, so I will be applying to fall 2023. Uh, yeah, for a PhD position in fall 2023. And I want to like continue this work on like compressed models. And I also want to think of like fairness, accountability, transparency, interpretability, robustness, privacy in such settings. Yeah. I think compressed model is like very important, because you also need your even though you might have your machine learning model trained, you also want it to be um, deployable as such. Yeah.
Yeah, awesome. Do you have anything else to add before we wrap it up?
I have nothing to add. Yeah.
Awesome. This was a pleasure having you over for the second time. Hopefully, we have you over more frequently now. And I hope that we make our trip to NeurIPS. I'm trying to
Sure.
get on it, and uh, if that is the like, it's going to be an amazing week. Uh, yeah, thanks a lot, Rakshit, for doing this, taking out time, and yeah, the paper was amazing. The explanation was great. So thanks a lot for all your advice in the end as well. And
Sure. Yeah. Thank you so much for having me. Yeah. I'm super excited for our New Rips trip. Yeah. If it does happen. Yeah.
yeah, hopefully, fingers crossed. Yeah.
Hopefully, fingers crossed.
Thanks a lot, everyone, for joining in. I'll see you in the next one. Bye.
Thank you. Bye bye.